Welcome back, ladies and gentlemen. Okay, the purpose of this next set of videos is just to give you nothing more but problem solving in all of the various topics that we've talked about in, let's say, the last 2 weeks, right? So this is going to be a video, in this one is going to be self-contained about just what we call these more advanced circuits, as well as the loose end that we tied up with capacitors and what happens when they happen to be in series and parallel. And so we'll build ourselves an advanced looking network of these things and make sure that we're all on the same page about that. Following this video will come another one that talks again about waves and optics, okay? And I've condensed them into these videos instead of having one big video where you have to watch 40 or 60 minutes or something and try to, find the piece that you need, because if you're on it with one topic but not for the other topic, this can get quite cumbersome. So I figured this was the easiest way to do it in small bites and small chunks. So hopefully you agree. If not, then I apologize. So let's jump right to it, shall we? Okay, so this is one of our more advanced circuits, okay? Let's take a look at it. It's got a couple of different branches here. We have a top branch with some current IC and a resistor R1, a lower left branch with a battery and R2, lower right-hand branch, battery E2, R4, and then in the middle, which is shared by the lower left and lower right branch, a resistor R3, okay? I denoted for you where all the currents are, okay, and all their respective directions, and they're listed out as A, B, C, D, X, and Y, okay? Most of the resistors are given. R2, R3, and R4 are given. IC, IA, and IB are given. Here, I want us to find lots of different quantities. So that means we're going to have to do lots of different loops, lots of different little techniques to get this in, okay? But namely, we want the two batteries, the top resistor, the two middle branch currents, IX and IY, and then the current that goes right up to connect from the bottom branch to the middle branch, ID. Okay, you can solve this any way that you like. There's literally lots and lots of different ways to try to attack this problem. So again, I will try to start from what I always say: if you can do, you do it, right? This is, we clearly identified this is not one of these problems where we are trying to find all the unknown currents, okay? Instead, we actually happen to have some of the currents, not all of them, but we have some of them, okay? And so I don't think it's going to be as complicated as some of the ones that we did in the previous video where we didn't know any of the currents. But there's lots of loops, so we do have to be careful. In particular, we tend to usually like to start with the top loop. And if we look at the top loop, this is one of the worst loops we can possibly start with, because we don't know R1, we don't know E1, and we don't know E2, okay? So strategically speaking, what do I always try to tell you? I try to say that if you don't have all the currents, the first thing you do is you pencil in, you assume a direction, and you give them a name and you pencil them in. If you do have some of the currents, though, do your best to try to trace out the junctions and see if there is maybe more information that you might not realize that you have at first glance that you can take advantage of. What do I mean by this? Let's start then. Pick your favorite junction, okay? I know here on this schematic that I'm given IA and IB. So I'm going to look for a junction where, if any exists, where IA and IB either come in or flow out, et cetera, et cetera. And if we look right at the bottom middle junction, okay, we see that IA flows in and IB flows in. So right away, we can exploit at the bottom middle junction, right, the fact that IA goes in, IB goes in, and what comes out is ID, which means right away then we have 3 amps plus 5 amps has got to be 8 amps. So ID is something that we actually now know. It's 8 amps. Great, so 8 amps is going to flow up to that middle connecting branch. But then it gets to the top, and some flows out as IY to the right, some flows out as IX to the left. And right now we're kind of stuck, at least for the moment. But we do know ID, so this one is now done, okay? Can we now figure out IX and IY? Well, we've just bought ourselves a new current, right? And we don't know what either IX or IY are, but we know they flow out of that junction, so we know that at the end of the day, whatever they are, they better add to be 8, okay? But let's just pick one of them and follow it. Let's follow IX, which goes to the left. Following it to the left, we get to another junction. What flows into that leftmost junction. We see that IX flows in. We also see, according to this picture, that IC flows in, and what flows out is IA. Well, that's great because we know IC and we know IA. IC is 2, IA is 3. The only way that 2 can flow in and 3 can flow out is if IX, therefore, has to be 1 amp. Do the same thing for IY at the right junction. So at the right junction, what do we have? We have flowing in is IY, flowing out, we have IB plus IC. We know IB and we know IC. This is 5 amps plus 2 amps, also known as 7 amps. So IY now is 7 amps. And what do you know? What did we say that had to be true about IX plus IY? They had to be ID, namely 1 plus 7 had to equal 8. The world is a happy place when it comes to currents, okay? So now if we rewind back to up here where we were, now we have all the currents. We have every current in every branch of this circuit. That's going to make our lives super easy. Now we just got to pick the appropriate loops that isolate in E1, isolate in E2, and R1. I've already started at the get-go saying that the top loop is probably not a good idea because it contains the unknowns E1, E2, and R1. So how about to find E1, use the bottom left loop. To find E2, use the bottom right loop, and then use any one that you want to find R1. So let's do that. So I'm gonna slightly zoom out here. And now I'm gonna do, since I did the junctions here in purple, I'm gonna do the loops in red. So I'm gonna call this the bottom left loop. And again, I'm gonna go in the direction that I've been doing since we started this topic. So I'm gonna start at that left junction, the purple left junction there. The first thing that I encounter is the current IA going across R2 in the direction of current. Then I come up the middle branch with ID across R3 in the direction of current. And then I go across the battery E1 in the proper direction, and I'm back home. I know all of these quantities now since I know all the currents. So the only known unknown here is E1. And we see that E1 then is just going to be IA R2 plus ID R3. Going back up and looking at our numbers, IA was 3, R2 is 4, 12, ID was 8, R3 was 3, 24, a 36 volt battery. By the same token, I'm going to do the bottom right in order to isolate E2. Okay, so that means I'll be starting from the place where IX and IY flow out of. And again, I'll do it in the same direction of evaluation. This time I flow against the current ID R3. I then flow against the current IB, and that was an R4. I then go across the battery in the wrong direction, and I'm back home. And so this then tells me that E2 is ID R3 plus IB R4. Plugging in our numbers, we already did ID times R3. That was 24. IB, though, is 5. R4 is 6. 30. This is a 54 volt battery. Cool, cool. The only unknown then is R1. We can now use the top loop if we want, since we know E1 and E2, or we can use the outer loop. I'm going to choose to use the outer loop, using the outer loop. And again, starting from the top, very top left, the first thing that I encounter is a minus IA R2. And then I come up the right-hand side and I go against the current IB R4. And then I go with the current IC R1, and I'm back home. Again, I know everything here except for R1. IA times R2, we've already have a number for this, negative 12 plus 30. minus IC. Let me just zoom back out here and remind myself what IC was. IC was 2. We combine negative 12 plus 30 gives us 18. Positive 18 is equal to 2R1. Divide out the 2 and we get R1 is 9 ohms. And so we have all the pieces that we wanted of this, again, very imposing looking circuit at first glance. But what we see is if we go step by step, and again, we ask ourselves the question, if we're given some of the currents, can we, I mean, this is the most heavily that we've made use of the junction rule, right? Typically, we use the junction rule to find one current here or there when we can, or to use a supplementary equation when we're doing one of the ones with multiple equations and multiple unknowns. But here we've seen that we were able to make use of the junction rule over and over again. That gave us all the currents, and then we're just back to picking the proper loops. Okay. The next one that I want to do for this video, sorry, it's actually over here, okay? Which sounds like I'm lying to you. Because when I started the video, I said I wanted to do a problem about a network of capacitors in series and parallel. What if we had a really complicated one of them, right? But I figured if I'm going to do it for capacitors, why not do it for resistors too? And then we'll just switch it out, okay? So since we're most familiar with resistors, let's do that one first, right? Here's a crazy network of 8 resistors, okay? Some are in series, some are in parallel with series, et cetera, okay? I want us to think about how we can decompose this. Again, what I mean by decompose is what one resistor, RT, can we replace this entire network of 8 resistors with such that it would be the equivalent resistance. We'll do that, and then after we do that, we'll say, what if these were all capacitors? Okay, that's the plan. Okay, let's see if we can make it happen. Okay, remember, we have to walk through these slowly because otherwise we'll try to get ahead of ourselves, and we have to picture ourselves like an electron and say, like, what can we do, this sort of thing, okay? So if we want to get all the way from R1 all the way to R8, if, let's just put some points on here, if we call this point A and we call this point B and we want to get all the way from A to B, the first thing that we have to do is go through R1. Everybody's going through R1. So R1 is definitely in series with something. Oh man, it's in series with something horrible. It's in something which is it's in series with the parallel combination of that mess at the top and R7. Everybody agree with that? It's the parallel combination of R2, 3, 4, 5, 6 and R7. Cool. That means if we knew what R2, 3, 4, 5, 6 was as one resistor, we would just have a simple parallel combination of that and R7. That parallel combination of the mess at the top and R7 is in series with R1. And again, that mess in the middle now that we're calling it is in series with R8. That's the big picture as to how we're going to do this. So let's deal with the mess at the top. Yes, I agree, the mess at the top has another parallel circuit in it. Not a problem, right? You can have parallels and parallels, just how you can have series and parallels and other things like that, right? But that's separate. That's its own top mess that we can find its resistance, and then we can use it in that middle part. What do I mean by that? When we get to this place, right, when we realize that this mess that I'm going to highlight here in red is in parallel with this mess, right, we're really saying that this entire piece that I'm highlighting in red could be replaced with a resistor R2, 3, 4, 5, 6, 7. And how do we get it? 1 over R2, 3, 4, 5, 6, 7 is really 1 over the top mess, which we called 1 over R2, 3, 4, 5, 6, plus 1 over R7. Okay? Now, we are clearly not ready. Okay? We know this one, right? This one's, yeah, cool. This one, though, we're not ready to do. So we need to resolve it. So what is it? Well, 1 over R2, 3, 4, 5, 6, 7. Let's go through this slowly. I'm sorry, 1 over R2, 3, 4, 5, 6. This one, let's do it in a different color, right? The green segment, right? 1 over R 2, 3, 4, 5, 6 is 3 branches in parallel. 1 over R2, 3 plus 1 over R4 plus 1 over R5, 6. Yes? The only one of these that we're really happy with is this one because that's the only one with a single resistor. But we're not so unhappy with R23 and R56 because what is R23 and R56, namely the pieces in purple, the purple segments? Do we all agree that, well, R23 is just R2 plus R3 because those two things are in series. If that's the case, then 2 plus 3, I'm sorry, R2 plus R3 is 9, which means that R56, 12 plus 24 is 36. And so what we have here then, plugging this in, is we have a 1 over R23, 1 over 9, plus 1 over 4, and R4 is 1, plus 1 over 36. Okay? And of course, when I made this, I picked stupid numbers because why wouldn't I do that? But nonetheless, actually, they're not so stupid, right? Because 9 does divide into 36. Good job, James. You got that one. Okay, so 9 divides 36 4 times. Okay, so with that, we can use a common denominator of 9. Okay, and so if we could use the common denominator of 36, right? This would be 4 of 36 plus 36 of 36 plus 1 of 36. This is also known as 41 over 36, which means that if we then want to take the inverse of this to get R2, 3, 4, 5, 6, then we see R2, 3, 4, 5, 6. That resistor is also known as 36 over 41, which you could convert to a decimal if you want, or you can just leave it as such. Okay, cool. Now we have the green segment resolved, but now remember where we were. We said that the green segment is the upper mess, right? And we use the green segment to get the red segment, 1 over R2, 3, 4, 5, 6, 7, by taking 1 over the thing that we just found and adding it to 1 over R7. So 1 over, and let's go back now and do that like we said in red. 1 over R2, 3, 4, 5, 6, 7 is 1 over R2, 3, 4, 5, 6 plus 1 over R7. And plugging in those numbers, this gives us a 41 over 36 plus 1 over 2, which does have a common denominator of 36. So we have to multiply this by 18 over 18. This is 41 plus 18 whole thing over 36, which is also known as 59 over 36. So again, we then need to take the inverse. R2, 3, 4, 5, 6, 7 is then a 36 over 59. And while we're at it now, why not get a decimal from this, because we're done with all of our, we are now completely done with all of our parallel combinations. And so that gives me about 0.61 ohm resistor, okay? We're close because now we have the red segment, and what do we see to get from A to B? The only thing left is that we have R1 in series with the red segment, in series with R8. So R1 and R8 are both 1. So then we finally see then that the total resistance is R1 plus R2, 3, 4, 5, 6, 7 plus R8, which is also known as 1, plus 0.61 plus 1, which is 2.61 ohm resistor. So despite all those crazy resistors in there, we could have replaced that entire 8 resistor mess with a single 2.61 ohm resistor. Okay, let's pause. No problem. If we can do it for resistors, we can do it for capacitors. All we have to do is remember the way that the resistor rules relate to the capacitor rules. How do the resistor rules relate to the capacitor rules? Let me remind you, right? The capacitor rules are identical to the resistor rules, just exactly reverse. So how resistors add in series is how capacitors add in parallel, and vice versa. So if we take this thing and think of all of them as this symbol, right? I'm not going to draw the whole thing out, but you get what I'm doing. Right? And now call this C7, C1, yada, yada, yada. 1, 2, 3 up here, right? Blah, blah, blah. You get how this goes, right? Once again, we're going to use the exact opposite rules, which means that that whole mess thing up in the middle is actually more friendly with capacitors than it is for resistors. Because remember, if capacitors in parallel act like resistors in series are nice. They're the ones that just add nice and easy. But this is going to be more annoying than we think, because the capacitors C2 and C3, as well as C2 and C3 are going to be in series with one another. C5 and C6 are going to be in series with one another. So it's going to be a mess no matter how we do it. Let's just go to the beginning, okay? So if we leave point A, we all got to go acknowledge that. That's no problem, okay? The first thing that happens then is that what we have to do then is that we have C1 is going to be in series with C2, 3, 4, 5, 6, 7, in series with C8, okay? So if that's the case, then we can write out the schematic in black. 1 over C total is 1 over C1 plus 1 over C2, 3, 4, 5, 6, 7 plus 1 over C8. How are we going to get that C2, 3, 4, 5, 6, 7? Well, that thing has two branches in parallel. Namely, that's going to be R 2, 3, 4, 5, 6 plus, oh gosh, I did it as R. That should be a C, plus C7. Okay, that would be nice. Again, if we knew what C2, 3, 4, 5, 6 was. Let's find out what he is. Well, that has 3 branches in parallel. That's the branch C2, 3 plus C4 plus C5, 6. And notice how this is already looking way different from the last one, because the parallel ones are the ones that are just adding across, as opposed to the series ones. To get this down, right? C2, 3, 4, 5, 6. To get this down to the next step, we now have to resolve what C2, 3 and C5, 6 are. And so finally, we have a place, and I'm just going to erase this for the moment now since we're done with it. Now we have a place to actually begin calculating some stuff. So let's do it. C23, 1 over C23 is 1 over C2 plus 1 over C3, because C2 is in series with the C3, and capacitors in series add like resistors in parallel. So if this is the case, this is then going back up to my numbers. This is 1 over 3 plus 1 over 6. That's nice because we have a common denominator of 6. So this is really a 2 plus 1 over 6, or 3 over 6, which means that C23 is nothing more than a 2 capacitor, or 2 farad capacitor. C5, 6, same token, 1 over C5, 6, 1 over C5 plus 1 over C6. Using our numbers for C5 and C6 is 12 and 24. 1 over 12 plus 1 over 24. Again, a common denominator of 24. This is 2 plus 1 over 24, which is also known as 3 over 24, which means that C5, 6, when we take the inverse, C5, 6 then is going to be 24 divided by 3. This is going to be an 8 farad capacitor. Again, I'm just going to get rid of the answer from before because we've already done it. Cool. So if we have C5, 6 and we have C2, 3, then we can get C2, 3, 4, 5, 6 from up here. That is going to be 2 plus 8 plus whatever C4 was, and C4 was just 1. 11. Oh God, 11 is going to make for an awful number in a denominator, but that's what I get for choosing these at random. Okay. Therefore, if we have C2, 3, 4, 5, 6, okay, we can now use that to get C2, 3, 4, 5, 6, 7, because C2, 3, 4, 5, 6, namely the mess up top, is in series with C7. So this is then 11 plus C7, which is 2, which is thus 13. Oh, I'm making my life worse and worse, but good thing I made C1 and C8 as 1s, because then finally we can take this last thing and see that 1 over CT, which is equal to 1 over C1 plus 1 over C2, 3, 4, 5, 6, 7, plus 1 over C8 is 1 over 1 plus 1 over 13 plus 1 over 1, which is going to be 13 plus 1 plus 13 whole thing over 13. 13 plus 13 is 26 plus 1 is 27 over 13, which means that if we take the inverse, the total capacitance then CT is 13 over 27, which is more than good enough to leave the result as such. But if you don't like working like that in terms of fractions, then we can just take our calculator, give ourselves the fraction 13 divided by 27 is going to be about 1. That's nice, about 0.1. Okay. Oh, that's not correct at all. That is not correct at all. I typed in the wrong number. 13 divided by 27. There we go. That's better. Had to be closer to half. It's 0.48. And we have it. So that entire mess of things in terms of a capacitor network comes out to be nothing more than just almost a half of a farad. Ladies and gentlemen, if you can do it for resistors, you can do it for capacitors. Okay. More importantly here, okay, more importantly, how did we do this? We went through it step by step. Took anything that was more complicated than 2 resistors or 2 capacitors and broke it into what its equivalent capacitance or equivalent resistance was, and then followed that down the chain as far down as we possibly could. If you could do one this complex, you could do one either then more complex or less by literally just following the same exact rules. Next video is going to have more problem solving on waves and optics. That way we have everything that we need for our last couple rounds of homework. As always, ladies and gentlemen, if you have any questions, comments, complaints, or concerns, please do not hesitate to send me an email. I hope you found this video informative, and I hope that you have a fantastic weekend.